Okay, everything is ready. It's time to start, right? Okay, hello everyone. Thank you for coming. My name is Victor Kropp. I'm software developer at JetBrains. You can find me at Kropp on Twitter and my website, Victor Kropp name and weblog. I'm a software developer, so most of the time I develop software. So I'm a programmer. Occasionally I visit conferences and talk about things that I like, that I find interesting. And one of such things, one of these topics is asynchronous programming in Kotlin with coroutines. Well, I know it's a bit lengthy, so let's break it down. So first, what is Kotlin? The main page at kotlinlang.org says that Kotlin is statically typed programming language for modern multi-platform applications. Well, when Google announced first-class support for Kotlin on Android roughly a year ago, for many people, Kotlin and Android became synonyms. Well, it's not. Well, it's true, but it's not it's not all. Kotlin can be used everywhere. It was started as an alternative language for JVM, Java Virtual Machine. And then quickly after the first release, we added support for compiling Kotlin into JavaScript so that you can write a web service, both backend part in Kotlin and front-end part, the application that runs in browser, also in Kotlin. And there is now Kotlin native backend in development, which will allow us to compile Kotlin to native binaries to run them on any desktop application system, Windows, Mac, Linux, on embedded devices with ARM processors, like, I don't know, Raspberry Pi, and so on. And it will allow us to write application for iPhone, for iOS, using Kotlin. So soon you will be able to share your business logic between iOS and Android. And this is the last time I say Android in this talk, because everything I will show applies to all targets that Kotlin can be compiled to. Then next is asynchronous programming. Well, this is the thing we all need to do, at least sometimes. But I rarely or never met a person who genuinely loves asynchronous programming, because it's hard. It usually involves a lot of ceremony around, and it is hard to handle errors. There are libraries that help to overcome these difficulties, but like, I don't know, RX Java. But they require you to change your mindset somehow. You need a lot of to put a lot of effort into doing even simple things right with such kind of libraries. It's very hard to read. They have a steep learning curve, and yeah, so usually what do we do when we need to fire some long computation and then get a result? We invoke some function and pass a callback to it. And then we soon find ourselves in callback hell. Have you seen this in your code, in some code bases? It happens quite often. Or there are other nightmares like shared mutable state. So we first parallelize our computations heavily, but then we put a synchronized block inside and then everything is blocked. It's hard to find bugs in such code and so on. I will show how coroutines make it easy. So what are coroutines? I don't want to go deeply into details. I will better focus on showing how to use them. And the most So the simplest explanation of what coroutines are is that coroutines are lightweight threads. I don't want to wave hands much. Let's get straight to the code, to the two examples. So let's start 100,000 threads. This is simple code in Kotlin. So I hope that everyone here in the audience knows Kotlin at least a little bit. If you don't understand something in the examples I will show, raise your hand, wave it. I will explain the samples we will see. So here we start 100,000 threads with a thread helper function. Each thread will sleep a second and then print a dot. That's it. We can run it. And yeah, we have some dots, but we've seen in the very beginning we got out of memory error, unable to create new native thread. Well, that's an expected outcome. You cannot just run 100,000 threads on commodity hardware. At least each thread requires a stack, and stack can be 1-2 megabytes, depending on implementation, on operating system. So with 16 gigs RAM on this laptop, I can at most run 16,000 threads if I need it. Okay, and let's check what we have with coroutines. So the example is very similar. We, instead of thread, we use launch helper. Instead of thread sleep, we have delay. Here, we print a dot. As in the previous example, we also need to, after starting our coroutines, we need to join them. The API here is similar to what we have with threads. Otherwise, coroutines are treated in the same way as daemon threads. So if there are no active, if we not wait for a result, the application will just exit. So let's check it out. We see there is no exception, and I will not count all the dots, but believe me, there are 100,000 of them. So this code runs perfectly. And also I put a measure time millis helper here to measure how long does it take to create 100,000 coroutines and to wait until they all finished. So it's 1 second and 244 milliseconds. 1 second is the delay we put inside. Everything else just took 244 milliseconds. Our coroutines run almost without any overhead. How do they do that? What's the difference between the threads example and the coroutines example? Well, the main difference is in delay function. When we call thread sleep, we effectively block a thread for a certain period of time. Nobody can use this thread. All the resources allocated for this thread are blocked and unusable. But with coroutines, when we call delay, we suspend this coroutine. We suspend this function and resume it after the delay. The thread is not blocked, and it can run something different, another coroutine. So coroutines do not introduce anything new to Java virtual machine. Kotlin is known to be interoperable with the earlier versions of Java. Uses all the existing capabilities. The coroutines are just, well, some kind of objects that can run some code, resume suspend, and resume sometime later when the result is ready, when the timeout is over, and so on. Let's take a look to a more realistic example. So here I have an example. I want to list a number of contributors for Kotlin repositories on GitHub. To do this, I use retrofit library. I created a simple API. It's not full, but it's enough for our purpose. It has only 2 methods. And, well, we first require all repositories for Kotlin user. We do it synchronously in this example. We use execute, and which will block the calling thread and wait for result. We get a result, these repositories, and then for each repository we invoke another API method to get a number of contributors. Let's run it. Wait a little bit. So it works. It lists all the repositories and their number of contributors there one by one. But there are some problems with this code. It runs synchronously and it blocks the calling threads. So let's take another approach on this, and this time we will use Asynchronous API. We use the same methods to get repositories. We then, instead of execute, we queue the request and provide a callback. On response, we get the response body, and then for each repository listed, we again call contributors, provide callback. On response, we get a result, a number of contributors, and then we print it. And you see this? This is what I've been talking about. This is callback hell. It's just starting. It's the entrance gate. Because we only have 2 nested callbacks. If we want to make some other API calls, so I don't know, for example, we don't want just get a number of contributors, we want to get their full profiles and their repositories, other repositories they contribute to, for example. We can easily nest much more callbacks. The other, first let's check it out. How does it work? It works much faster because all requests are queued and parallelized behind the scenes. But this code, this simple example, has become absolutely unreadable. There are a lot of boilerplate here. You have a lot of repetitive parameters here. I don't know. It's very hard to follow the business logic. Also, and we didn't even add any error handling here. So this on failure callback is empty. So how can we do better with Kotlin and coroutines? I have another example, and this time we will use a wait pattern, which is widely used and known in languages like C#, Python, newer versions of JavaScript. And in those languages, this async await stuff was introduced as a language feature. However, in Kotlin, we can add, we implement it as methods in utility libraries. And we can add our own await methods for third-party APIs. We'll see it later. So, in this example, it is almost identical to the first one, except we have a await here instead of execute and get body. And this await, do you see it? It's too small. It returns list of repositories. So it returns the raw result type you needed. It's not some wrapper, it's just it. So our code is clear, easily understandable, and if we run it, it works as expected. But you may have noticed that it prints all the lines one by one. It is sequential now. It looks sequential, and it is sequential even though it doesn't block the calling thread. It runs all the requests on the background threads. So if we were in some kind of different environment, like on the server, the thread is unblocked and can process other requests. In order to parallelize it, to make it asynchronous, we put the same launch block we've seen earlier here inside the loop. If we run it again, then it works much faster because all the requests are parallelized. So with coroutines, you decide when to make your code asynchronous or not. It's very straightforward and explicit, and it is an important property. To make this API even more idiomatic, Kotlin, as we like to say, we can change the API methods. So this, I'll make it here this way. So this repositories method returns list of repositories, and the trick is that it is suspendable function. We'll get back to it in a moment. So now our code looks like any other sequential code, but under the hood it is suspendable, and it works asynchronously. There is a marker on the left-hand side in the IDE that shows us that at this point in the method body, it can be suspended and resumed later after a result is ready, and thus the thread will not be blocked. So this is how we can write better APIs in Kotlin. So, okay, let's get back to the presentation shortly. So, with 100,000 threads, we got unable to create new native thread exception. 100,000 coroutines work just okay. How do you implement this suspending function in your code? So, we always saying that Kotlin is fun because there is a fun keyword everywhere. So you declare every function with fun. With the coroutines, you now can suspend fun. Well, with the multi-platform project, you can also have expected fun and actual fun. But that's a topic for another talk. Okay, suspendable functions. So to make a function suspendable, you put a keyword suspender and call suspend coroutine helper function. This is the function provided by standard library. It is somehow implemented inside. The interesting part here that this is a special call that makes a suspension point in this point inside the method, and Kotlin compiler transforms all the code following this line in your method body and puts it in a callback or continuation in the API. So under the hood, it uses the same technique of fire method, provide a callback, and then do all this stuff with the result inside this callback. But it is hidden. It is all this done by the compiler behind the scenes. This is, by the way, this is the most low-level stuff I will be showing today. and in most cases, you do not need to write it by hand. I said that all this async await stuff is implemented as helper methods in Kotlin. And the only language feature is the suspend keyword, and meaning because these are all functions, they are already implemented in many libraries. So we provide support for converting existing APIs to suspendable APIs for Java 8 Futures, for RX Java, and many other libraries. And also there are third-party implementations, like, for example, for retrofit library I mentioned. There is already an implementation of await function. But what if we want to implement it by ourselves? So we invoke suspend coroutine and get a continuation. What do we need to do next? Next, we do the same stuff as we would done to actually do our task, what we want to do here in this method. But in the end, when the result is ready, we are obliged to call invoke continuation to resume the original method. So in this case, our await method returns result of type T. This is what suspend coroutine returns. You see in this example, and this is the value which we need to resume continuation. So we, as I said, we doing the same stuff as we did before. We enqueue our request and provide a callback. And on response, we resume the continuation with the result. In case of an error, we can resume continuation with exception. For the calling code, it will be absolutely transparent. So you call a suspending function, like any other function, and like from any other function, you either expect that it will return a result or it will throw an exception. This is what will happen when you use coroutines. So this code look just the same as we've seen, but it is hidden inside the library. You write it only once, you do not repeat it, or you better use the already existing third-party implementations. Okay, so we have suspending functions, which can suspend at some point of time. This means that the function that calling suspending functions can suspend as well. So they are should be suspendable, marked with suspend keyword as well. You see chicken and egg problem here? Our public static void main, the entry point to any program, is not suspendable function. How do we start suspending computation? Each call is denoted by marker. We start suspending computation using coroutine builder. We've seen one of it before. It is a launch builder. It's a kind of fire and forget coroutine starter. It starts coroutine and doesn't care about the result. It's kind of void method. It only returns a job. We've seen job.join call. So this is an abstraction to control the execution of coroutine. We'll see some more later. There is also async coroutine builder for async await pattern, where you expect a result and it returns a deferred. Deferred is a Kotlin term for future. Kotlin is multi-platform language, and on different platforms there are different names for futures. For example, in JavaScript you have promise, Java 8 completable future and Guava listenable future and so on. So there are many names for them. So Kotlin team had to choose the name that is not used anywhere yet to avoid clashes, and they choose deferred. Deferred is like any other future, similar to them, and it also implements a job, extends job, so you can control the execution of async block as well. And there is another useful builder, run blocking. I've used it before. You may have noticed it. It starts coroutine in the same thread where it was called, so thus it effectively blocks the thread. This is why it's not just run, but run blocking, to be explicit about it. Since it blocks the thread, it returns a raw result without any wrappers and without any control, because when it finishes, the coroutine is finished already. It is useful for demo purposes and for testing. So you want to test all your code, and with run blocking you can test your coroutines. We've only seen these builders without parameters before, but they can accept some parameters. The most important is the first one, where you can pass a dispatcher. So for example, if you have a Swing application, you only can modify Swing components from the Swing thread. Then you need to put your coroutine then you need your coroutine to be invoked by Swing dispatcher. To it under the hood will reschedule the coroutine on Swing thread using invoke later. It is absolutely transparent for you. Also, there is similarly there is UI dispatcher on Android. I said it. Sorry. Then never mind. Then there is async. Async, just an example. And there is a common pool dispatcher, which is actually a default dispatcher. It runs coroutines on fork join thread pool. And by the way, you can create your own thread pools and your own dispatchers as well. And there is also an unconfined dispatcher, and this is a dispatcher that doesn't reschedule any computation on different thread, and it continues execution on the same thread where continuation resume was called. It is useful for short-living very small tasks to avoid penalties of rescheduling. Let's take a look on an example. So what we have here, here is a number of coroutines starting, and let's execute it and check results. So I'll explain one line by line. First, we print thread name in run blocking, and it's main because run blocking blocks starts coroutine in the same thread where it was called. Then we have two lines with the common pool. These are they. This proves that common pool is default dispatcher. Then we create new single thread context. So this is how we can run coroutines on our specific thread. This is my thread. Then again, we have a line executed on main thread. This is this one. Because we launch coroutine in with unconfined dispatcher, it runs the coroutine on the same thread. And then we have this default executor. This line, it is invoked after delay. So delay suspends the coroutine and resumes it later. And in order to resume it after some timeout, it needs a scheduler. Scheduler by default runs on on its own thread, default executor. And if you really need it, you can provide your own implementation here as well. No, but here what we've seen that we can have the same coroutine, this one, to run across multiple threads. So it started on one thread and resumed on another. The same can happen with the coroutines running on common pool. They can start on one thread and be resumed on the other. Okay. So it was not exactly true that the first parameter of builder is a dispatcher. It is a coroutine context, and coroutine context can contain many things. One thing useful for debug is that you can provide a name for a coroutine. Let's take a look on it. This is another a little bit smaller example. The interesting part is here in the middle. We use launch at common pool and with context function on common pool. The difference between them is that launch launches another coroutine, and with context uses the same coroutine but with a different context. So we started it on a main thread, but then this block was executed on a fork join pool, common pool. But we only see the thread name here. What we can do for debug purposes, we can go to run configuration and add -d Kotlin X coroutines debug option and run the same example again. And now there is a coroutine name appended to every thread name. Coroutines are numbered, so we start first coroutine, it runs on main thread and it's coroutine number 1. Then with launch, we launch the second coroutine, it runs on the common pool and it's coroutine number 2. And then with the context, we have the same coroutine number 1 running on the common pool now. So you can specify a different name, so like regedev days, for example. And now all our the coroutine number 1 has RDD number 1 name. It is useful for debugging purposes. And you can also combine contexts with simply with the plus, because Kotlin has operator overloading, and it's just very useful in this context. So we changed the context to common pool and with the different coroutine name, and this is what we see here. And then on the next line, it's back again to RDD, because this line is executed with the original context. Okay, so we can modify contexts. Coroutine context is available inside every coroutine. It has some predefined properties, like dispatcher name. There is a job for this coroutine available also inside the context. And it also can hold any user data. Similar to thread local storage in case of threads, if you want to save something that will be available throughout the coroutine, you use coroutine context. The only difference is that coroutine context is mutable, while thread local storage is mutable. But coroutines are so cheap and the context is so simple that you create a new one when you need it, when you need to change something. Okay. We only launched our coroutines before, but what if we need to cancel them? different things may happen. We may not need the result anymore. So we start a coroutine that prints a line every second, and then after a delay of 2.5 seconds, it cancels. It is cancelled, and we need to join it to actually wait until it is cancelled. Let's run it, 1, 2, and then cancelled. The interesting thing here inside a coroutine, we do not have any code that handles this cancellation. Well, except this delay. Probably it does the thing. Let's comment it out. And we see, so we should wait 2.5 seconds. Probably they are already, well, yeah. It was a delay function that checked for cancellation. We can do it ourselves. There is active property. So when the coroutine is not active, it is when the coroutine is cancelled, it is not active, and we put break here. Let's check this. And yeah, it is cancellation was handled gracefully. You cannot always use break, like because you don't have a loop every time. So you can throw cancellation exception. Here, this is a special exception that is handled by the framework in a different way. So it's a valid reason to end the coroutine. It's not propagated as an handled exception. And this is how you can exit any nested coroutine if you need it. There are some convenient shortcuts. For example, you can cancel and join in one call. And since this timeout pattern is very popular, there is a helper function with timeout to do the same thing. Okay, next thing is how do we combine our coroutines? So we've seen before either we do it sequentially and wait for result every time, after every call, or we can launch a bunch of coroutines. So let's take a look at another example, and this is this one. So we start 3 coroutines with different latencies. They will return the answer after 2 seconds, 1 second and a half second. And if we await them all 3, then the result will be the slowest one. So if we first put 1.await, then we will wait for 2 seconds, while the result for second and third coroutine will be ready before. For this we can use select clause. This is again not the something that is built in the language. It's rather a library function. It builds sort of DSL for coroutines manipulation. So we can, for example, await a result of a coroutine, and select will select the first available clause inside this block. So in our case, the second coroutine will finish first, and it will be ready first, and select block will select it and will print 2 as expected. You can also since this DSL is just a regular Kotlin code, here I start 5 coroutines and put them into a list, and here inside the same select block I can put on await clause on every coroutine in a loop. And after a random delay, the first available result is selected. In this case, it's 4. Okay. Next, we've seen only a single result before, but using the same suspending function, we can implement a channel pattern similar to what we have in other languages. So here I have a producer coroutine that produce a number from 0 to 10 after delay. Each after a delay of half a second, it sends it to a channel producer. And next, in an infinite loop, I consume the result with receive. And each half a second, it prints a next number. And actually, since this is an infinite loop, at the end, it throws an exception that channel was closed when I want to receive the number that is not there anymore. Of course, the RAM means to check it. I will not show it right now because I have a lot of more to show. For example, there is a dual pattern, and this is consumer or actor in the library, in coroutines library. It is an opposite. In infinite loop, it receives values from channel, and here we send values from 0 to 10 in this channel. So here it was without a delay. And we haven't seen an exception here because we exited earlier. And okay, that's it. So with the only language features of suspending function and a bunch of library functions that can be written by third-party developers that can be improved over the time, we got a support for many different programming styles, for programming patterns, for channels, suspending functions, asynchronous computations, and so on. And with the same thing, we can build a generator pattern. So, for example, in C# and Python, there is yield keyword to create a generator function, function that returns a lazy sequence of values, which are evaluated one by one as soon as they are needed. Here we build a sequence of Fibonacci numbers. This is the algorithm you all know. The interesting part here is this yield. It is a function that suspends execution of this sequence generator and passes it to the caller method. Let's see how it works. So here, of course, I can use any collection stuff available in Kotlin or anything, or just use for each to iterate. But I want to make it explicit. Here, I am using iterator to put separate print statements here, and what I wanted to do to show you how it really works. So I will put an exclamation mark before yield. So before the iterator will get the next value and print it. And what we get here is that we now have an exclamation mark before every number printed. You see, here is an exclamation mark, it is in one method, and here we print number, it is another method. because this sequence generator is suspended after each value it generates and resumed when the calling thread needs another value. It doesn't resume. We haven't seen an exclamation mark at the end because it didn't resume after we exited this block and consumed last value we needed. Okay, I have some few minutes more, and there is another thing. Even coroutines are cheap. You can run a coroutine for each small task you have. You can pass everything there in context, or I don't know. You can run thousands of coroutines. Sometimes, if you really need to provide some excess of control, you might want to run your coroutines on a single thread to prevent any asynchronous issues, concurrency issues. But you can also use mutex, different mutex implemented in Kotlin coroutines library. The difference from the standard library is that this mutex has with the log function, which is suspendable. So you no longer block the thread in which you are waiting for mutex, but you suspend computation and then release it when the mutex is released. Okay. You may have seen that coroutines are an experimental package, and Kotlin makes coroutines experimental. What does it mean? It doesn't mean that it is not ready to production yet. You can use it, it is ready, it is performant, there are no performance issues or whatever. The only difference is that some APIs are not final yet, and we expect them to finalize them and put everything into standard library, so in Kotlin coroutines instead of Kotlin X coroutines experimental very soon. But we already use them, and many people around use them. You can check out many blog posts on the internet. There is a framework for building web applications with coroutines, Cater.io, built from ground up with the coroutines. So coroutines are at the heart of the framework. You can use coroutines with the Spring. Spring guys often talk about this. Check out on YouTube. There are a lot of talks available there. And well, the last what I want to share, this is some links. Coroutines, by example, you may check the interesting more examples on how to use coroutines. There is also some low-level stuff available in a design document for coroutines. If you want to dive deep into the details, how it works. And with this, thank you very much, and enjoy the rest of the conference.
Well, we have 1 minute for one question.
Can you please say something about coroutines and application servers?
What kind of information do you need?
Application servers handle their own threads, so you do not create threads if you work with application servers.
Yeah, I've shown that there is, for example, Swing dispatcher. It also reuses the utilities provided by Swing, for example, and there is invoke later in dispatcher, and delegates the execution to Swing. So you can write your own dispatcher for any third-party service library and so on that will take coroutine, intercept all continuations. So before resuming, continuation resume inside behind the scene calls delegates. The execution to interceptor, if there is one, this dispatcher, and it dispatches the continuation on the thread it wants. So either common pool or some third-party existing pool of threads. As I said, one of the biggest keys of success of Kotlin is that it interoperates well with all existing libraries, and you can write your own extensions to any library you want.